So you can see that in both 1's complement representation form and 2's complement representation form, what you have learned is that negative numbers, the sign of the number is indicated by the MSB bit. So when the MSB bit is 1, it indicates for negative number. When MSB bit is 0, it indicates positive number. Yesterday, last time I had started with binary arithmetic of 2's complement in 2's complement representation. So if you look at the third column, okay, in this table, you can easily see that each successive 2's complement number all the way till plus 7, they can be obtained by adding 1 to the previous one, ignoring any carries beyond the 4th bit position. You see, when you add 1 to a number, it gives you the next successive number. Okay. And whenever there is a carry, we have to just simply ignore it. As in case of when we go from minus 1 to 0, minus 1 to 0, and you move from minus 1 to 0, carry is generated. So we simply ignore that carry. And you see, so each number can be obtained by just adding 1 to the previous one, ignoring any carry beyond the 4th bit. Okay. So we can, so with this, we can, it is clear that we can simply apply the normal, very basic binary rules, addition rules, and we can perform the arithmetic or addition of binary numbers represented in 2's complement form. So in the last class, I had taken 2 examples also. And I had given one question as homework as well. Have you people tried that? So let us look at the example. In the last class, I had taken a simple example of 3 and 4, addition of 3 and 4 in 2's complement representation form. So you see, in 2's complement representation form, we know that in order to represent number 3, you see this can be written as plus 3 adding with plus 4. Okay. And plus 3 in 2's complement representation form is 0, 0, 1, 1. Plus 4 is 0, 1, 0, 0. So when you add these two, you have to apply simple addition rule. When you add these two, what you get is, we start from the LSB bit. So 1 plus 0 will give 1, 1 plus 0 gives 1, 0 plus 1 gives 1, 0 plus 0 gives 0. So what you get is, you see, now to check whether the result is positive or negative, you have to check MSB bit, right? So here MSB bit is 0, which indicates that the sum is positive number. Okay? And the value of the number is, you just take the decimal equivalent of this result. So this is, answer is plus 7. You see, 0, 1, 1, 1 is binary equivalent of decimal numbers. Okay. Now, yesterday I had given one question as a homework. It was adding
6 plus 3. 6 plus 3.
6 plus 6 plus 3. Okay. Let us see this solution for this question. Okay. Now, plus 6. Plus 6 is 0, 1, 1, 0. This is how we write plus 6, right? Plus 6 in 2's complement form. You see, first MSB bit is 0, indicating that it is a positive number. And if you see the decimal, find the decimal equivalent of this binary number, it is equal to 6. Then plus 3. So plus 3 will be 0, 0, 1, 1. So let us add them together. So when you add them, you get 0 plus 1 is 1. 1 plus 1 is some 0 with a carry. When you add these two 1, you get some 0 with a carry. When you add 1 plus 0 plus 0, you get 1. So the result here, if you see, what it is indicating, it is saying that what we were expecting. We were expecting answer to be equal to plus 9. We know that answer is 9. When you add 6 and 3, I have taken very trivial example. we know it has to be plus 9, but when you add this, what you are getting is MSB bit as 1, which indicates the negative number, right? But the result should not be negative. So the reason here, see, this is giving, this is not the correct answer actually. It is saying it is a negative number, and the value of the number is, you know that whenever a decimal number is represented in negative form, it is in the 2's complement form, right? So it means its value is, you take 2's complement of this, which means 1, 1, 1, 3, right? So it is 2's complement. So it means the answer it is saying is, answer is minus 7, which is not correct, right? We should have got plus 9, not minus 7. Now this has happened because there is an overflow. There is an overflow here. It is because of this problem that it is giving incorrect answer. Now, what do you mean by overflow? First of all, let us see what is overflow. So if an addition of...
Ma'am, can't hear you properly.
Yes, ma'am.
Now is it now audible? Yes, a second. Audible now?
Yes, ma'am.
Yeah.
Right? Okay. So let us first of all understand what is this overflow problem. I said this is giving wrong kind of answer because of overflow problem over here. Now, what is an overflow problem? Now, if an addition of operation produces a result that exceeds the range of number system, then we say that there is an overflow. Okay. What is meant by this? Let me just explain. Okay. What I mean to say is that now here we have taken 4 bit. We have represented each decimal number using 4 bits, right? We know that we require at least 4 bits to represent these two numbers, isn't it? How you know that? Because we know that the range of numbers which can be represented using n bits in 2's complement representation form is from minus 2 raised to power n minus 1 to plus 2 raised to power n minus 1 minus 1, right? So if we take n equal to 4, the range becomes minus 2 raised to power 3 means 8 to plus 7. If you had taken, if instead of 4 bits, if you would have expressed these two numbers in 3 bits, was it possible to express? With 3 bits, we know that the range of numbers which can be expressed with 3 bits is from minus 2 raised to power, instead of 3, n will write 3, so 3 minus 1 is 2. So it will be from minus 4 to plus 3 only, right? So it means we require at least 4 bits to represent plus 6 and plus 6. Plus 3 can actually be represented using 3 bits, but we require 4 bits to represent plus 6, right? And what is the range that can be represented using 4 bits? We require 4 bits. This is what we have seen here, right? So what is the range? Range is from minus 8 to plus 7. But the result, if you add 6 and 3, it gives result as 9, right? We know that 9 doesn't fall under this range. Our range with 4 bit is minus 8 to 7. 9 is not falling under this range. And therefore, it means that we require one additional bit, right? To represent 9, we actually require 5 bits. With 4 bits, we cannot represent 9. Because with 4 bits, the range of number that can be represented is minus 8 to plus 7. So to represent plus 9, we actually require 5 bits, right? So since result is out of this range, so we call this problem as overflow problem. Okay. Now, how to read the answer correctly when it is an overflow problem? We'll see that first. Okay, and then I will explain you how to identify that this is an overflow problem or not. This is a very trivial example where you already know that 6 plus 3 has to be 9. So answer is wrong, right? But then we must know, the circuit that you develop should understand, should tell you that it's an overflow problem, right? So we'll look at that also, how to identify that it's an overflow problem. Okay, but before that, let us look how to get the answer correct, how to interpret this answer correctly. Okay, so whenever there is an overflow problem, for example, in this case, 6 plus 3, there was an overflow problem. You should always, whatever sign it is indicating, here it is indicating that result is negative, right? So you must understand that it is giving the wrong, sign. So although it is saying negative, but result is positive. result is positive number. Okay, positive. Why I'm saying it is positive? Because it's an overflow case. So whenever there is an overflow case, whatever sign the result is indicating, you have to take this sign just in. Okay, so it is here in this example, it was showing that result is negative. So it means the result is positive. So if this result is positive, what is the value of this number? Value of this result will be simply it is in true form, right? So you just have to find the decimal equivalent of this, which means 8 plus 1 equal to 9. So it is plus 9. Is that clear what I have done? Whenever there is an overflow problem, whatever result the addition gave, you must understand that it is giving the false, it is telling the false sign. So you have to just assume the sign to be reversed. Okay. For example, in this case, when you added 6 with 3, result was showing the sum was showing the result as positive, negative number, right? But we know that it's an overflow case. It means it is a positive result. Okay. So answer is positive, and whenever the result binary number is in positive form, it means you can find the value by simply, adding the weights corresponding to 1 bit, right? So you get result as plus 9. I hope it is clear. Yes.
Yes, ma'am. Yes, ma'am.
Let me take one more example. Let's take one more example. Let us say, let's say minus 6. Okay. I'm doing minus 6, minus 3. Okay. Minus 6, minus 3. So in the last class, I was saying that, in subtraction, whenever there is a subtraction problem, the circuit designed for binary adders can be used to perform binary subtraction if we change the problem of subtraction into addition, right? So this is minus 6 minus 3. We will write it in this form, minus 6 plus minus 3. Okay. Now let us solve this. So we know that plus 6 is 0, 1, 1, 0, right? Plus 6 is 0, 1, 1, 0. Okay. So minus 6 will be minus 6 in 2's complement form. Okay. We are doing 2's complement arithmetic, right? So minus 6 will be, we start from the MSB, retain the MSB as it is, retain the next consecutive bits also as it is until you encounter first one. So the first one has to be written as, has to be taken down as it is, and then rest all bits should be inverted. So 1 will become 0, 0 will become 1. So this is minus 6. Okay. Now let's write plus 3. Plus 3 is 0, 0, 1, 1. So minus 3 will be, tell me quickly what will be minus 3?
1, 1, 0, 1.
Right. 1, 1, 0, 1. Okay. So what we did, we have written LSB bit as it is. Since we have encountered first one, next all bits are complemented. So 1 has become 0, 0 has become 1, 0 has become 1. Okay. Now the question is minus 6 plus minus 3. Okay. So let us solve it here. So minus 6 minus 3, we have to add them, right? So minus 6 is 1, 0, 1, 0. Minus 3 is 1, 1, 0, 1. Okay. Let us add them. So 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1. And 1 plus 1 is, yeah. And 1 plus 1 is 0 with a carry 1. Now you tell me what has to be done with this carry?
Discarded.
It has to be simply discarded. As I said, in 2's complement arithmetic method, whenever there is a carry generation, we simply have to ignore it. Carry generation at the MSB bit, at the last bit. If there is a carry generation at the MSB bit, you have to simply ignore it. Okay. So this is the result that it is showing. But now we know that this is an overflow case because answer we know here it has to be -9, right? Answer has to be negative because we are adding two negative numbers. But what is the result showing? It is saying that it is a positive result, right? Because MSB bit is 0, right? So it means, and we already know it's an overflow case. I will let you know how to identify that later on. But it's an overflow case, we know it, right? So it means that, yes, it means that this result is saying that it is a positive number, but actually the result is negative, right? Because we know that it's an overflow case. So from on that basis, we are saying that the result is negative. Okay. Although MSB bit is 0, but we are saying result is negative because we know it's an overflow case, right? And what will be the value of this result? What is the value? To get the value, you just have to take the 2's complement of output. So value will be 2's complement of 0, 1, 1, 1. That is 1.
1
I'm
0
writing
0 1.
let's keep it first, then 0, 0, 1, which is binary equivalent of decimal number 9,
9.
right? So answer is, it means answer is -9. Why minus? Because result was showing answer to be positive, but since it is an overflow case, we said result is negative. Okay. And if the result is negative, what is the value of the result? You take 2's complement of the result. The 2's complement of result is 1001, which is binary equivalent of decimal number 9. So answer is -9.
Ma'am,
Right? Yes.
ma'am, previously we took binary equivalent and here we are taking 2's complement for the final answer. So
Right.
why such a variation?
It is because in the previous case, result was positive, right? We said answer is positive. So you know that in the table, if you look at the table, see, let me go to the table. See, this is the table. If I tell you, if I ask you, let me change the color. If I ask you what is this indicating, what will you?
Take 2's complement of it.
You have to take 2's complement of this. What is 2's
Yes,
complement
ma'am.
of this? It is 0,
0
1,
0 0 1 0.
0 0 1 0, right?
Yes, ma'am.
0 0 1 0 means this is binary
Minus
equivalent
2.
of decimal number 2. So it is -2, right? So if I give you
Yes,
a binary number, binary sequence, which has MSB bit as 1, which means it is a negative number. So to find the value of that number, what you did? You have computed the 2's complement of this, right?
okay, ma'am. Yes.
Right? So when I'm saying that result is negative, you see in this case, here result was negative, right?
Yes, ma'am.
Result is negative. So we have to find the value of this result, you have to take 2's complement. Is that clear?
Yes,
So when
ma'am.
the result is negative, to get the value of that result, take 2's complement. But when the result is positive, no need of taking 2's complement. You have to directly write the decimal equivalent of that binary sequence, right?
Okay, ma'am. Thank you, ma'am.
Okay. So you see, when can overflow happen now? Overflow can happen during addition of two positive numbers or when you add two negative numbers, right? If you add one positive number and one negative number, will you ever get an overflow? No. Overflow is what?
No.
When your sum goes out of the range, right? Out of the range defined by that number system, right? So when your output is when your output is expected to go out of range, if you add two positive numbers or if you add two negative numbers, only in that case sum will be, because sum will be greater than the two addends, isn't it? So overflow happens only in two situations. It may happen only in two situations, either when you are adding two positive numbers or when you are adding two negative numbers. Addition between a positive and negative number will never lead to overflow problem. Okay. And the simple way to detect overflow is by looking at the sign of MSB bit. Is looking at the MSB bit. Okay. You see, for example, in this case, this is what? This is the case of -6, -3, right? You see here, both the numbers are negative. So the MSB bits are 1, right? Here also MSB bit is 1, here also MSB bit is 1 because both the numbers are negative. But the result is expected to be negative, right? Isn't it? When you add two negative numbers, result is expected to be negative. But if you look at the sum, if the sum is starting with 0, it means result is positive, isn't it? That is not possible. When you add two negative numbers, your result has to be negative. So if you check the MSB bit, the sign bit of the two addends and the result, if they do not match, it means there is an overflow. Am I clear? You see,
Yes, ma'am.
overflow is only going to
Yes, ma'am.
happen. It can happen only when you add two positive numbers or when you add two negative numbers. As an example here, the previous example, we were adding two negative numbers, right? And it was resulting into overflow. So how to detect that there is an overflow? A simple way would be to check the MSB bits. When you add two positive numbers, both the MSB bit will be 0 and the result MSB bit has to be 0, right? When you add two negative numbers, both the numbers MSB bit has to be 0 and the result should also start with has to be 1 and the result should also start with 1, right? But if you look at this previous example, -6 and -3, we were adding -6 and -3. -6 is starting with 1, -3 is also starting with 1, indicating that these are negative numbers. But the result that you obtained was starting with 0, indicating that result is positive, right? Which cannot be true. When you add two negative numbers, your result should also be a negative number. So it should start with MSB bit 1. So if there is this kind of conflict, it means there is an overflow. Is that clear?
Yes, ma'am.
Yes.
Yeah. If you look at the previous example, the last example, previous to this example, I had taken an example of addition of +6 and +3, right? So +6 was 0, 1, 1, 0, +3 was 0, 0, 1, 1. Both the numbers were starting with MSB bit equal to 0, right? Because they are positive numbers. The result we expect to start with 0, right? Because both the numbers, when you add two positive numbers, your result has to be positive, right? Positive result means MSB bit should be 0. But here, in this example, we found that result was 1001, which was starting with 1 bit, which means it's an overflow problem. Is that clear? Okay. And you know what to do when there is an overflow problem. Whenever there is an overflow problem, you have to consider the sign of result to be opposite. Okay. And then accordingly, you get the value of the result. Okay. Now, another way to find out overflow case is to compare the carry into and coming out of MSB bit. As an example, let us take example of this +6 and +3 only. What is the carry going to MSB bit? MSB bit is this, right? The first bit. Okay. So what is the carry going into MSB bit? It is 1, right? This is what is carry going into MSB bit. What is carry coming out of MSB bit? Is there any carry generation
0.
in this example? No. So it
No,
is
ma'am.
0, right?
No.
C out is 0. So if C in is not equal to C out, it means it is an overflow case. This is another way to identify that whether there is an overflow. I will repeat again. You have to compare carry going into the MSB bit and carry coming out of the MSB bit. If they are not equal, it means there is an overflow problem. Okay, so carry in and carry out, if they are not equal, it means it's an overflow problem. This is another very easy way to identify whether there is an overflow or not. This is very easy to implement in hardware also. Okay, can you suggest something? How can you implement this this condition in hardware? Suppose you had been asked to add a hardware in the circuit which will identify whether there is an overflow or not. How will you do it?
We could keep overflow flag so that if
But
it's on, then
how it will get you tell me the hardware that you will use. Flag is okay. That will flag becomes equal to 1 in overflow. When it is 0, it means. But what kind of hardware can we use? you can use a simple XOR gate, a 2-input XOR gate. And the inputs to the XOR gate will be carry going into MSB bit and carry coming out of MSB bit. You know that XOR gate, it gives output equal to 1 if the two inputs are unequal, right? So one input to XOR gate is C in, other input to XOR gate is C out. And when these two bits are different, it means there is an overflow. Output of XOR will be 1. So XOR output being equal to 1 means overflow condition. XOR output equal to 0 means there is no overflow. So this logic is very easy to implement in hardware. You simply require one XOR gate. Okay. Fine. I suppose it is clear now how to perform addition.
Yes, ma'am.
Let us take one more problem. Let's say adding 7 plus 7. So I'll write plus 7 plus 7. Okay. Now, if I say we have to represent these numbers in 4 bits, okay, we can represent plus 7 in 4 bits. Minimum number of bits required to represent plus 7 will be 4 bits, right? With 3 bits, you cannot represent plus 7. So let's represent plus 7 using 4 bits. So plus 7 is 0, 1, 1, 1, right? You see MSB bit is 0, means it is positive number, and 1, 1, 1, 0, 1, 1, 1 is binary equivalent of number 7. So this is plus 7. Adding it to plus 7. So 0, 1, 1, 1. Plus 7 plus 7. 0, 1, 1, 1, 0, 1, 1, 1. If you add them, 1 plus 1 is 0 with carry 1. 1 plus 1 is 0 with carry 1. Then you add 1 to that sum. So you get 1 as a sum and carry it. Again, same situation, 3 ones. When you add 3 ones, you get 1 as a sum and carry as a 1. And the MSB bit addition will give 1 plus 0 is 1. What is carry out? Is there any generation of carry at the MSB bit position?
No.
1 plus 0 plus
No.
no carry. So carry out is 0. Is it an overflow case or not?
Yes.
It's
Yes,
an
ma'am.
overflow case. This C in is not equal to C out. C in is not equal to C out. It means it's an overflow case. So when it is an overflow case, as I said, you have to consider the sign as opposite, right? Now the result is saying that sum is negative, right? MSB bit is 1. So it means since it is an overflow, we will say that answer is positive, not negative. Answer is positive. And when the answer is positive, how do you find out value of the number? You simply find the decimal equivalent of that binary sequence, right? For positive numbers, you simply have to find the decimal equivalent of that binary sequence. So it will be 2 raised power 0, 2 raised power 1, 2 raised power 2, 2 raised power 3. This is equal to 8 plus 4 plus 1, that is 14. So answer is plus 14. Is this clear to all of you?
Yes, ma'am.
Okay. How will you do 5 minus 7? 5 minus 7. How to perform addition, this addition? 5 minus 7 you have to do. How to do it? You have to do plus 5 plus minus 7. So I hope it is clear now. Whenever there is a subtraction problem, you have to convert it into addition problem. Right? Why we are doing this? So that same hardware can be used for performing both addition as well as subtraction. Okay.
Ma'am,
Yes.
could
Solve
you
this
please
problem.
do 8 plus 8?
8 plus 8. Okay. Plus 8 and plus 8. In 2's complement, you see, right? 2's
Yes,
complement
ma'am.
representation. How do you represent plus 8 in 2's complement form? Plus 8. How many bits will be required? We know that with
5.
4 bits, with 4 bits, what is the range of number that can be displayed with 2's complement? It is -8 to
-8 to +7.
+7. It means to represent +8, we require how many bits? We require at least 5 bits, right? With 4 bit, we cannot represent +8. It is out of range, right? So we require 5 bits, at least 5 bits, okay? So we will take n equal to 5. So +8 will be 0, 1, right? +8 is 0, 1. If you add them, what do you get? 0, 0, 0. 1 plus 1 is 0, with carry 1. So this is 1. Carry in is 1, carry out is 0, right? Carry in is 1, carry out is 0. What does it mean? It is an overflow problem, right? So you tell the what should be the answer? Answer should be 16, right?
Yeah.
Anybody got?
Yes, ma'am.
Answer has to be, it's an overflow problem. It means,
Yes.
although it is saying negative, answer is
Positive.
positive. Although it is saying negative, answer is positive because it's an overflow problem, right? So if it is a positive, answer is positive, it means what? You simply have to take decimal equivalent of
Decimal
this
equivalent.
binary sequence, which is +16. Is that clear?
Yes, ma'am.
Okay. Now let us move to 1's complement arithmetic. Okay, this was 2's complement arithmetic, where we have seen that you simply have to apply the binary addition rule. You can simply, add two binary numbers that are represented in 2's complement representation form. But you can perform the addition by using the simple binary addition method, with the exception that whenever there is carry generation at the MSB with position, you simply have to ignore it, right? Now let us look at 1's complement arithmetic. Okay. We'll look at addition and subtraction. Subtraction in 1's complement. In 1's complement representation. Okay. Let's look at addition and subtraction in 1's complement representation. For that, let me again go back to the table. Okay. Let me again go back to that table. We know how to represent positive and negative number in 1's complement form, right? The MSB bit has to be 0 if it is a positive number, MSB bit has to be 1 if it is representing a negative number. And then if you start counting from -8, from -7 right through +7, you can see that each number is obtained by simply adding 1 to the previous number, right? This is -7. -7 in 1's complement form is 1000. If you simply add 1 to this, you get 1001, which is -6, right? So each, successive number is obtained by simply adding 1 to the previous number. Okay. Only thing is that when you move from 0 to 1, okay, when you move from 0 to 1, that is from here to here. Okay. Will you get 0001 if you add 1 to 1111? No. If you add 1 to 1111, if you add 1 to this, you will get answer in 5 bits, right? Isn't it? So you get in 5 bits. What is the next? What you should have got? You should have got 1, right? 1's complement, decimal number 1, right? When you add 1 to 0, you should get 1. That means 0001. But what you are getting? We get when we add 1 to this 1111, which is representing 0. And you add 1 to it, you get 10000. That is in 5 bits, right? So what to do? You simply should In 2's complement, we had just discarded this one, right? Whenever the number of bits was increasing, going from 4-bit to 5-bit, we simply ignore that last one, carry, right? But here in 1's complement form, what we are doing, we have to add this 1 to the LSB bit. So what you get is 0001, which is decimal number 1. Is that clear? What I'm saying? Right?
Yes, ma'am.
Okay. So what I mean to say is that whenever you get, while doing the binary arithmetic, addition of two binary numbers, you have to apply the same rules, simple rules of, binary arithmetic, unsigned binary arithmetic. But only thing is, whenever there is generation of carry, at the last bit, at the MSB bit position, you have to add that carry to your result. Okay. This is also called end around carry. Called end around carry. Okay. You simply add that final carry to the sum. Okay. So we will use this, this concept, and let me take some examples now. So I'll take simple problems now again. Very easy, simple problems, and then we'll move to some difficult problems. Okay. So let me take very simple problems. Let's say 3 plus 4. Okay, very simple problem. 3 plus 4. So we have to write plus 3 plus 4. Okay. 3 plus 4. So let's do this. So 3 plus 4. So plus 3 is 0011 plus 4 is 0100. This is a very simple problem. So we start from the LSB bits. 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. Result is positive because MSB bit is 0. Okay. So its answer is positive. So plus, to find the value of the number, you simply have to find the decimal equivalent of this binary number. So it is 0111, which means 7. So answer is plus 7. Okay. Let us take 6 minus 3. Okay. Question is 6 minus 3. So as I said, we will transform this problem into addition problem. That means plus 6 plus minus 3. Okay. So let us do this. So plus 6 is 0, 1, 1, 0. And plus 3 is 0, 0, 1, 1. Right? This is normal binary representation. Minus 3 will be, now we are doing 1's complement arithmetic, right? So minus 3 is represented as 1's complement of plus 3, right? So minus 3 is 1, 1, 0, 0. Now let us add. So this is the question. Okay. So let us add now. Plus 6 minus 3. We are going to add them. Right? So plus 6, we have seen it is 0, 1, 1, 0. Minus 3, we have seen it is 1, 1, 0, 0. Right? So let us add them. So 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 1 gives sum as 0 and carry as 1. 1 plus 0 plus 1. There are two ones. So 1 and 1 will give sum as 0 and carry as 1. Right? Now, because there is a generation of carry, so this carry has to be added over here. So what do you get? You get 1, 1, 0, 0. So result is positive. There is no overflow case. You see here also concept of how identification of overflow is same, the way we did in 2's complement representation arithmetic. Okay, you have to look at C in and C out. They are same, means there is no overflow, right? So, but only difference is that if there is generation of carry from the MSB bit position, you have to add it to the result. So you get 0, 0, 1, 1. Okay. So 0, 0, 1, 1. Which means answer is positive. And the value of answer is, you simply have to find the decimal equivalent of this binary, which means 2. Clear to everyone?
Yes, ma'am.
Yes, ma'am.
Okay. Then quickly do this sum. -3 -6. Do it quickly. -3 -6. And let me know if all of you got the correct answer or not. -3 -6. We'll convert this into addition problem. -3 plus -6. +3 is 0 0 1 1. Anybody got?
Zero 1 1 0.
Are you getting correct answer?
1 0
Yes,
0
ma'am.
1
Zero
0.
1 0 0 1.
0 1 1 0.
Okay. See here.
0 1 1 0.
-3. How do you write -3 in one's complement representation form?
1 1 0 0.
1 1 0
Right.
0.
1 1 0 0. -6.
1 1 1
0
0.
0 1.
1 0 0 1. Right. So we have to add -3 and -6. -3 plus -6. This is the sum. Right? Which means we have to add 1 1 0 0 and 1 0 0 1. So let us add them. So it gives 1 0. 1 plus 0 is 1. 1 plus 1 is 0 with the carry 1. Right? Now you see here, first thing to note is that MSB bit में carry going was 0 and coming out is 1. It means it's an which case?
Overflow.
Overflow. This is an overflow case. Secondly, we know that whenever there is generation of carry from the MSB bit position, you have to add it. Okay. So we'll add it over here with the result. So what you get, 1 plus 1 is 0 with carry 1. 1 plus 0 is 1. This is 1 and this is 0. This is the result. Result is showing answer is positive, but we already know that it's an overflow problem, which means answer is negative. So answer is negative. To find the answer, you have to take 1's complement of this result, right? 1's complement of result is 1001, which is decimal equivalent of 1001 is
9.
9. So answer is
-9.
-9.